butt joint for a boiler shell. So I think we discussed all these things. There are two kinds of joints in case of a boiler fabrication. They are longitudinal joint and circumferential joint. Generally, the longitudinal joint is a butt joint, and the circumferential joint is going to be a lap joint. So why? Because butt joint will have a more strength when compared to the lap joint. So since the longitudinal joint requires more strength when compared to the circumferential joint, so always the longitudinal joint is going to be the butt joint. So and also most preferable joint for boiler longitudinal joint of the boiler is a double strap triple riveted butt joint. So this is the most preferable. Maybe sometimes based on the requirement it may change, but most of the cases this is going to be the preferable joint in case of this longitudinal joint for a boiler shell, which is a double strap. Means there are two cover plates. Triple riveted means there are three rows of rivets for each plate. Again, there are different pitch values also. People will follow that. We'll discuss those things while designing the joint. So I think we already discussed all these things. Yes, this is the general or preferred joint in case of a boiler. So for longitudinal joint, see, you can see here it is a triple riveted double strap butt joint with unequal straps. See, you can see that here this is the outer strap and this is the inner strap. You can see that the width of the outer strap is smaller when compared to the width of the inner strap. So here we will call it as unequal width straps or unequal straps. So in this case the design is different. Why the design is different? Because you can clearly see that here this rivets are this row of rivets and this row of rivets, they are subjected to only single shear, because this row and this row is covered by only single cover plate, whereas the remaining rivets they are covered by double cover plate. So we said it is a triple row double strap. So double strap means two cover plates. Triple row means, see here from this point, this is a section here or seam. So this side you have one plate and this side you have another plate. See, for each plate 1, 2, 3. For this bottom plate you have 3 rows. Even for the top plate also you have 3 rows. So that's why we call it as triple riveted. Again in those 3 rows, 2 rows are subjected to double shear and 1 row is subjected to only single shear. And also here while designing that, like I already mentioned in the previous problem, if there is a repeating section is there, always the design is based on the repeating section. If the repeating section is not available, then we need to consider all the rivets in the joint. So here he has given a section view. So that means it's not the total joint here. So he has shown only a part of the plate or part of the joint. So therefore in this kind I can easily identify that. So there is a repeating section. So now if I take this one as my repeating section, see the same thing is repeat. Okay, not this one. This entire thing I need to consider. So or else, okay, if this is not there, okay, I'll consider this is my repeating section. See, if I take this one as one section, then I can similarly I have the similar kind of repeating section here and similar kind of repeating section like here, and it will go continuously something like this. So therefore I need to design the based on this repeating group or repeating group. We'll call it as a repeating group. In case of repeating group, here in case of this triple riveted double strap butt joint with unequal straps, how many number of rows are there? Number of rivets are there. Of course, number of rows are only 3. So number of rivets for a repeating group. So 3 plus 2, 5 rivets are there. Out of that 5, 4 are subjected to double shear. These 4 are subjected to double shear. Only this one, this outer row is subjected to single shear. So that means, so while estimating the shearing strength of the rivets, you need to consider these 4 rivets are under double shear and this one is in the single shear. And also one more thing what you can observe is, if you look at the pitch in the outer row, this is the pitch in the outer row, and the pitch in the inner row is, I can take either distance between these two, this one and this one. See, this is also same. So this pitch and this pitch. Inner row pitches is same, but outer row pitch is, you can see that it is larger than the inner row pitch. Or I can say, in other words, the number of rivets per pitch length in outer row is half of the number of rivets in the inner row. So if I take this one as a pitch length here, you can say in this is the condition. So how many rivets are there in the outer row for the pitch length? For this, if I take outer pitch length here, this is P. So how many rivets are there in this length? How many rivets are there? Anybody guess? In the outer row, that means in this row, how many rivets are there in this length?
3 rivets.
Huh? Enama?
3, sir.
3. ఒరే ఏం చూస్తున్నావు నువ్వు? అవుటర్ పిచ్ లెంత్ అంటే ఈ సెంటర్ లైన్ నుంచి ఈ సెంటర్ లైన్ వరకు ఎన్ని రివీట్స్ ఉన్నాయని అడిగాను నేను. 3 ఎట్లా ఉన్నాయి నీకు? 3 కనబడుతున్నాయి అక్కడ. ఈ సెంటర్ లైన్ నుంచి ఈ సెంటర్ లైన్కి వి కాల్ ఇట్ యాజ్ పిచ్. సో విత్ ఇన్ దిస్ పిచ్ లెంత్ మొత్తం రోలో ఎన్ని ఉన్నాయని కాదు అడుగుతుంది నేను. విత్ ఇన్ ద పిచ్ లెంత్ హౌ మెనీ నంబర్ ఆఫ్ రివీట్స్ ఆర్ దేర్? Somebody said something. I understood. Any? Let us say some number 1, 2, 3, 4, whatever. Somebody is told 2, 3. That is wrong answer. Other than that, any other guess? So, అరే మీ డయాగ్రామ్ కనిపిస్తుంది దాంట్లో ఎన్ని రూట్స్ ఉన్నాయి కూడా చెప్పమంటే కూడా చెప్పలేరా మీరు? ఇంకా ఇంకేం
ఉన్నాయి సార్, హాఫ్ ఆఫ్ ఉన్నాయి సార్.
So there are only one rivet. There are only one rivet because within this length. So whatever I drawn here, so this side we have only half rivet and this side you have only half rivet. So the total you have only one number of rivet only within this pitch length in the outer row. If I take inner row, how many rivets are there? Within this pitch length there are 2 rows, 2 rivets are there, 2 complete rivets are there. So there are 2 rows. So then here, if I go to this, how many rivets are there?
2.
For this also 2. So that means only in the outer row, or I can say this condition as the number of rows in the outer row is half of the number of rows in the inner rows. So inner rows you have 2 rows, 2 rivets. Outer row I have only 1 rivet. So therefore the number of rows in the outer row is half of the number of rivets in the inner rows. So this is the case. This is a standard one. If you want to design a triple riveted double strap butt joint with unequal straps, so why you will take in the outer row, why you are taking less number of rivets is because of this outer row is close to the edge. So now if I have more number of holes in the outer row, this will weaken the plate in the tearing strength. So that's why to avoid this, we'll go for less number of rivets in the outer row. Okay. So these are the things you need to remember while designing this rivet joint, that is longitudinal butt joint for a boiler shell. So that is for boiler longitudinal joint, which is nothing but a butt joint, and that too double strap with unequal strips. So here clearly you can see that also the pitch in the outer row is P. If I take pitch in the outer row is P, then the pitch in the inner row should be P/2 only, half of this. That's why outer row will have half of the number of rivets in the inner rows. So therefore obviously your pitch will become half in the inner rows. Similarly here I need to consider this margin here. So margin is default. In all the joints generally we take margin as 1.5D. So that you will get from the data book. If you don't know that, you can refer our data book. Similarly, what is this PT value? So this PT value will depend upon again what type of riveting pattern you are using in the joint. So here for inner rows, what type of riveting pattern it is? It is not a chain riveting. You can see it is a zigzag riveting. So it is going something like this. For inner rows, it is a zigzag riveting. So for zigzag riveting, you have one value for PT. For chain riveting. So we have another formula. So that is also given in the data book. So for all these things, see now onwards, if you want to design this riveted joints, whether it is for a longitudinal butt joint or circumferential lap joint, we have to heavily dependent on the data book, because all the whatever maybe the equations or standards, they are given in the data book only. So we need to depend upon the data book only. So therefore, so based on this, what you can do is you can identify this PT value also. Once I have defined all the parameters for this, so then what we'll left with is T we already calculated either based on the Unwin's formula or that is equating the shearing strength of the plate to the crushing strength of the rivets. So that you can do that. And then this thickness T1, that is the thickness of the cover plates. So if it is T1, so that for that also is given the formula in the data book only. So you need to verify data book to pick the formula for this T1, that is thickness of the cover plates also. So like this, so we need to design that. So now we'll see one by one step. So rivet, and T is the thickness of the cylindrical wall. So that's what we estimated. So both should be in mm only. So then if when the thickness of the plate is less than 8 mm, the diameter of the rivet is obtained by equating the shearing resistance of the rivets to the crushing resistance. So this is the one more important point. So that means the diameter of the rivet is estimated either two ways based on the thickness of the cover plates. If the thickness of the cover plate is more than 8 mm, then you need to use Unwin's formula. If it is less than 8 mm, you need to equate the shearing strength of the rivets to the crushing strength of the rivets or crushing strength of the joint. So that means in order to find the diameter, so you need to equate the shearing strength or shearing resistance and the crushing resistance. That means I need to estimate what is the shearing resistance and I need to estimate what is the crushing resistance in case of this joint. So let us assume if the thickness is less than 8 mm, how I can proceed? If it is more than 8 mm, it is straightforward equation only. So you can easily estimate the diameter of the rivet simply taking this relation. I have a T value. If T is more than 8, simply I'll use this relation. I can directly calculate the D value. But if it is less than 8 mm, then only you need to follow this procedure. So you need to estimate what is the shearing resistance of the rivets to the crushing resistance. So how I can estimate the shearing resistance and how I can estimate the crushing resistance. So for that, like I already told at the beginning, this shearing resistance or this crushing resistance are estimated based on the repeating group. So I need to identify the repeating group. In the repeating group, how many rivets are there? So again, in those number of rivets, how many rivets are subjected to single shear? How many rivets are subjected to double shear? So I need to find that. So based on that, I can calculate what is the shearing strength of the rivets. Rivets is that repeating group. Similarly, when comes to the crushing, we don't bother whether it is a double shear or single shear. In case of crushing, simply you need to identify what are the total number of rivets in the repeating group. Then you need to estimate what is the crushing strength of those things. So based on that, we will find what is the diameter of the rivets. So for that here, in the next, so this is the second way of calculating it. So I'll tell you, I'll show you how to do that in next case. But one more important point is whether you are using either the first Unwin's formula or whether you are using this criteria. That is, you are getting the diameter of the rivet by equating the shearing strength of the rivets to the crushing strength of the plate or rivet. So whatever may be the approach you followed, in both the cases, it has to satisfy this condition. That means always the diameter of the rivet should be less than the plate thickness. So you cannot take the diameter of the rivet more than the thickness of the plate. So this is the one more check you need to follow. That means either I can use this point A, that is either I can use the Unwin's formula, or I will use this criteria, that is equating the shearing resistance to the crushing resistance. From that I will get the D value. So then I need to check this value whether this D is less than T or not also. Suppose from the calculation if I get the D is more than T, then the design is not correct. So as per Indian boiler regulations, you need to take always the diameter of the rivet is less than the plate thickness, you need to make sure that always your D should be less than T. If that is not the case, again you need to redesign your joint. So that means you need to change the thickness of the plate again. So then again you need to do the calculations for D like that. You need to repeat the things. So now if I come to this one, okay, then after that the diameter of the rivet hole is slightly more than the diameter of the rivet. So we know this. The standard sizes of boiler rivet and the corresponding rivet holes are taken from the data book. So again here the thing is the standard size of boiler rivet and corresponding rivet holes, like I already mentioned. So we have a table 9.5. Maybe in the previous class, I think I already referred that. So how to find the standard diameter and then its corresponding hole diameter also. So that is table 9.5 only. So from the table 9.5 only, I need to pick here. If I calculate the diameter of the rivet, so from that diameter of the rivet, so let us say I got some what I can say diameter of the rivet as, let us say some using either this equation or using Henry's formula, I got 18.25 mm. Diameter of the rivet, I got something like this. So then simply I cannot take this way as the final diameter. So what we need to do is we need to use the data book again. From the data book you need to pick the standard values. So if you refer the table 9.5 again, so if I got 18.25 mm as the diameter of the rivet from my calculations, so then I need to pick the standard value from the data book. If you look at the table here, I need to pick the diameter of the table as, instead of 18.25 mm, I need to take the standard value, next standard value, which is 20 mm from the data book. If you see the table 9.5, so in that after you have 12, 14, 16, 18 and 20. So I cannot take 18 because here I got 18.25. So I cannot go lower value. I always have to go for the higher value. So then instead of 18, I have to take 20 mm. If I take 20 mm is the diameter of the rivet, then the diameter of the rivet hole should be 21 mm. So that is also given in the table. The table 9.5 you are given, that is also given. So that means, so here be careful. So only for thickness you can take in the values. So then once you decided the thickness value, then the diameter can be estimated in in two ways. That is based on the thickness of the plate. If the thickness of the plate is less than 8 mm, you need to follow one formula. If the thickness of plate is more than 8 mm, you need to use Unwin's formula. So again, if you calculate it based on these two, either of these two, so not all two, because you may have thickness either less than 8 mm or more than 8 mm. If it is more than 8 mm, I will use Unwin's formula, I will calculate thickness. If it is less than 8 mm, I will equate the shearing strength to the crushing strength, I will calculate the diameter. Then, once you got the diameter, first check what you need to do is, you need to verify that whether your diameter of the rivet is less than the plate thickness or not. You need to check that. Then after that, you need to take the standard value. But that standard value is, so you need to identify the two values. One is for the diameter of the rivet, another one is for the diameter of the rivet hole. So that those things you have to pick from your table 9.5. So you have in the table 9.5, you have two rows. That is, first row is nominal diameter of the rivet in mm. Second row is diameter of the rivet hole, that is also in mm. So diameter of the rivet is denoted by D dash. So that's what we in the beginning we discussed about various terminologies or what are the various notations followed. That D is denoted by diameter of the rivet hole. D dash is the diameter of the rivet itself. Okay, so like this I can find the diameter of the rivet and rivet hole. So alternatively, the diameter of the rivet hole can be obtained by the following approximate relations. This is also we already known to us. So this is the diameter. Okay, so here he has followed a different notation. So maybe in the textbook they interchange it. So D dash is here he has taken it as D dash is the diameter of the rivet hole and D is the diameter of the rivet. So diameter of the rivet hole is equal to D plus, I said in the previous class it is approximately 1.5 mm. So average of these two, 1 to 2 mm we mentioned means the average of these two is only 1.5 mm. So if you don't know how to pick the value from the data book, you can take this approximate relationship also. So that is the diameter of the rivet hole is equal to diameter of the rivet plus 1.5 mm. You can take that. Where d dash is the diameter of the rivet hole and d is the diameter of the hole. So like this, the second step is over in the joint. So that means first I'll estimate thickness of the plate, then I'll estimate the diameter of the rivet and rivet hole. Then the next step is I need to estimate what is this pitch values. What are the pitch values? This P, if I know this P, this is going to be P by 2 only. So I can do that also easily. Similarly, I need to estimate what is this PT and what is this M value and what is this thickness values. If I done that, everything is over now. So that means we estimated this T value, then we estimated the diameter of the hole and diameter of the rivet. Then next step is we'll go for the estimation of the pitch value. So that is the third point is pitch of the rivets. Okay. So as shown in the figure, the pitch of the rivets in the outer row is maximum. So that's what you can see that in this diagram here. In the outer row, the pitch is maximum when compared to the inner rows. So then the pitch of the rivets in the middle and inner rows is 1/2 of the pitch in the outer row. That is P by 2. That's what he has shown in the diagram. Also, you can see that inner rows pitch is half of the pitch in the outer row. Or in other words, I can say that the number of rivets in the outer row is half of the number of rivets in the inner row. Either way, you can say it. Whether this pitch is P by 2 and this pitch is P, or the number of rivets in the outer row is half of the number of rivets in the inner row. Means in the outer row for pitch length you have 1 rivet, for inner row you have 2 rivets. So either way you can state that one. So same thing you can state in 2 ways. So that's what the next statement here. The pitch of the rivets in the outer row is obtained by equating the shearing strength of the rivets to the tensile strength of the plate. So now this is the next condition. See, in case of finding out the diameter of the rivet, you need to equate the shearing strength of the rivets to the crushing strength. So if you have any confusion, so you can open your data book. In the data book also has clearly given those things. So don't worry whether I am able to remember all these things or not when designing it. So you don't bother about those things. If you open the data book, so that page number 9.3 is there in the data book. If you refer that, so first he has given the same thing, thickness of the boiler plate formula, whatever we discussed it. He has given the same thing, but he has not used that corrosion allowance. So sometimes we may neglect the corrosion allowance. That's why he has not given. So thickness of the boiler plate he has given it as T is equal to PD by 2 sigma T into eta L. So he has given. The second one what he has given is in the design particulars. If you look at that column, design particulars, so diameter of the rivet for T greater than 8. So which is given it as D is equal to 6.05 root T. In the brackets, he has written that unbiased formula also. So we have to do that. For T less than 8 mm, obtain D by equating shearing strength to crushing strength of the rivets. So that's what we discussed. So that means no need to remember it, but only thing is you need to follow this specified approach in designing this joint. So for that, you should have a data book. The data book is your guide. So use the data book. Based on that, you need to design the joints. But when come to this pitch of rivets now, what you have to do is here you need to equate the outer equating the shear strength of the rivets to the tensile strength of the plate. So you need to equate that. So from that you need to get the pitch value. Whatever value you got it, again that is not going to be the final pitch value. There are again limits for this pitch value. So that means as per Indian boiler regulation code, there should be some value, minimum value for the pitch. We call it as that minimum pitch. And similarly, there should be some value, maximum value for pitch also. That means always your pitch value should be within these two values. It has to be more than minimum pitch value. At the same time, it should be less than the maximum pitch value. So then, what is the minimum pitch and what is the maximum pitch? So that also you need to look into that. So for that, he has data book. If you open the data book, he has given that condition also. That is, minimum pitch is around 2.25 to 2.5 D. Your minimum pitch value should be 2.25 to 2.5 D. That is equation 9.4. If you refer your data book, equation number 9.4 is going to be 2.25 D. P minimum is equal to 2.25 to 2.5 D. Similarly, the maximum permissible pitch is also. Always these things are in mm only. So don't take other units for everything. Whatever we discussing, the units are only mm. Maximum permissible pitch in mm, P max is equal to C into T plus 41.28. What is the C? What is the T? What is T? I'll tell you. That again, that C is you have to pick from the data book again. There in the data book, you have a table 9.7 is there. In that 9.7, for each and every joint, he has given what is the value of C value. So, if you have a data book with you, just refer that table 9.7 in the data book now. So, after this 9.5, so earlier we referred to table 9.5. So, after that, you have 9.7 also. You can see that. Next page only, immediately, next page only, boiler code factor C, table 9.7, boiler code factor C. So then he has given that again, the C value is different for lap joint as well as for butt joint. Again, in case of butt joint, if it is a single cover butt joint, it is different value. If it is double cover butt joint, that is a different value. So now, again, it will depend upon the number of rivets also for pitch length. See, you can see the table here. So, I think I don't know how many of you are having data book and following this. What I do is, I'll show it to you so that you can, maybe, I don't know whether it is visible to you or not. Anyway, I'll try it. So, I think, is it visible to you? Maybe in the reverse way or properly it is visible?
Reverse, sir.
Reverse only. So,
Reverse.
because it is in
Sir,
it is, no, it is in the presentation. So if I remove stop presenting, so now you can see clearly now. It is not in reverse now, right?
Yes, sir. Yes, sir.
See, you can see the table 9.7 here. So here, this is the number of rows per pitch length. You can see here number of rows per pitch length. So that means how many number of rivets are there per pitch length. If it is 1, 2, 3, something like this per pitch length. So based on that, again based on whether our joint is lap joint or butt joint. Then again in butt joint, whether it is a single cover plate or you have a double cover plate. Based on that, you have a C values here. See, I'll show you those formulas also. Whatever we discussed so far. I'll show you all those formulas also in the data book so that you can learn all those things here. So these are the things. So this is the table we need to refer for designing boiler joints. So here you can see that clearly here. This is used for longitudinal joint of the boiler. So for boiler axially loaded structural joints. For boiler and axially loaded structural joints. So your longitudinal joint is subjected to a tensile load, so therefore that's why it is called longitudinal joint or axially loaded joint. See, the first one what he has given is thickness of the boiler shell. So what is the formula for that? Formula is given this side. T is equal to PD by, of course here the notations are somewhat different here. ST as used in case of sigma T, he has used ST. So this is the old version of the data book what I have. So in the new version, he has used sigma T only. So use that one. So this is the formula we need to use to find the thickness of the boiler plate. So then you come down. Here you can see that the diameter of the rivet. So details of diameter of the rivet will be here. So in that he has given the two conditions. So if the thickness is more than 8, we have to use unwinds formula. So he has given clearly here. This is the unwinds formula. Here you can see that this is the unwinds formula. Similarly, if the thickness is less than 8, you have written the statement also. You need to equate the shearing strength of the rivets to the crushing strength. Then after that, you have a condition on minimum pitch. So you can see that here, minimum pitch condition is he has given like this. Similarly, the maximum pitch condition also he has given like this. So we need to follow these things. So because everything is in data book, that's why I am insisting on the data book. If it's the data book, you cannot do anything here. Okay, right. So similarly, I showed you that here in the maximum pitch case. So what he has written here is P max is equal to C into T plus 41.28. Of course, it is 41 only. Maybe it is updated now. It is 40. It should be 41.28. Even if it is not 41.28, don't worry, don't bother about it. You can take 48 also. Only 0.28 means it doesn't matter. Right? So in the below is given the value of C, we can take it from table 9.7. Clearly mentioned that also. If you don't know what is C here, if you look at on the bottom of that equation, you can clearly see that the value of C can be picked from the table 9.7. Already shown to you what is table 9.7 also. Depending upon the joint, you need to pick the C value. So that means I have a condition for the minimum pitch value, I have a condition for the maximum pitch value, and I will calculate the pitch value. Actually, I will calculate the pitch value based on based on which condition I need to calculate the pitch value. Here, so I need to use pitch of the rivets in the outer edge obtained by equating the shearing strength of the rivets to the tensile strength of the plate. So now using this equation, I will compute the pitch value. Once I get the pitch value, then I need to compare this pitch, whether it is more than the minimum pitch or not, and at the same time it is less than the maximum pitch or not. Suppose if you got a pitch value which is less than minimum pitch value. So what is the minimum pitch value from the data book? We are taking it as 2.25D. Let us say 2.25D. So I already know the diameter of the rivet. D is known to me. So I calculate D is nothing but here diameter of the rivet hole in this case, or whatever it may be. It is not much deviation is there. You can take anything. Let us take, I got the D is equal to 20. Then 2.25 20 is nothing but for around 45. Minimum pitch should be 45 mm. But from this calculation, just by equating the shearing strength of the rivets to the tensile strength of the plate, let us assume that you got a pitch value which is 20 mm. So that means it is violating that minimum pitch condition. So your minimum pitch should be 45 mm. But from this calculation, you are getting only 25 mm. So then what you have to do is, you have to take the pitch as 45 mm only instead of whatever you got 25 mm from this calculation. We don't use this value because it has to satisfy the conditions. So therefore, I'll choose the minimum pitch value as, or the actual pitch value as the minimum pitch value, which is 45. Similarly, if I use this relation, that is P max is equal to C into T plus 41.28, something is there. So in that, so if I calculate that, I got the maximum pitch value is something, P max is 200 mm. But with this calculation again, so if I equating the shearing strength of the rivet to the tensile strength of the plate, if I got it as something like a 300 mm. Again, which is more than your allowable maximum pitch value. Allowable maximum pitch value is only 240 or 250 mm. If I use this equation, CT plus 41.28, if I use that formula, let us assume I got it as 250 mm as the maximum allowable pitch value. But from this calculation, what I got it is 300. So that means I cannot take the pitch value as 300. I have to take the pitch value only 250 mm only. So that means depending upon the value what you got based on this equation, that is equating the shearing strength of the rivets to the tensile strength of the blade, if it is higher than the maximum pitch value or higher if the value is whatever P value you got from this equation, if it is more than the maximum pitch value, you have to take the maximum pitch value as your pitch value. If it is less than the minimum pitch value, whatever you got the value from this calculation from this equation, if that value is less than the minimum pitch value, your pitch value should be the minimum pitch value, not the value what you got from the calculation. Right? So like this, you need to remember the things. So once I identify the P value, that is pitch value. So for that, first I need to compute these things. So first I have to compute P value based on this equation. Later I can verify it whether this pitch value is within that limits, that is between P minimum or P maximum. I have to verify that. So first we'll see this calculation, how I can estimate the shearing strength of the rivets and how I can estimate the tensile strength of the plate. Then by equating that, I'll get the pitch value. So what are the equations for that? So for this purpose, let us consider the plate length P. So that means we are considering only the pitch length. the tensile strength of the plate per pitch length in outer row of the rivets is given by. This is the formula. Why I will get this formula? Pt is equal to P minus D into T into sigma T. So how many rivets are there per pitch length? Just now I showed you that figure. So here in the outer row, how many rivets are there per pitch length? This is your pitch length. What you have showed here. In the pitch length, you have only one rivet, or else half of the hole is there in this portion, and half of the rivet hole is there in this portion. In the, if I take only a plate, I am talking about the plate. So plate will have hole. Only rivet is different. Plate will have a rivet hole. So therefore, here half rivet hole and here half rivet will there. If I add half plus half, it will become 1. So therefore, what is the material length in this? So in the total pitch P, you drill that one hole of diameter D. So therefore, the net width is P minus D only. Then of course, thickness of the plate we calculated as T. P minus D into T, that is the area which resisting the tensile load multiplied by the tensile strength, which is nothing but the sigma T. So from that you will get your tensile strength of the rivets in the outer row. So this is in the outer row. So PT is equal to P minus D into T into sigma T. So why I am considering only the outer row? Because so outer row is the weakest one. So in the tensile strength point of view, why outer row is the weakest one? See now if I take this row, if I want to take this row here, what happens is, in order to the plate to be sheared, teared off here in the middle row, first these rows should be sheared off. First, if these rows, these rivets are sheared off, then these rows, then only it is going to be teared off. Here the plate is going to be teared off. So that means obviously the shearing further shearing strength across this section. So for that, the shearing strength of the rivets also getting added here. Of course, if I consider the pitch length, I need to consider the shearing strength of the one rivet. So therefore, it is going to be more than this. So that's why always I'll take the tensile strength of the plate is based on the outer row only. So therefore, for that the formula is this one. Pt is equal to P minus D into T into sigma T. Then I need to compute shearing strength of the rivets. This I already told to you. The width of the inner strap is more than that of the outer strap. Therefore, rivets in the outer row are subjected to single shear. At the same time, the rivets in the middle and inner rows are subjected to double shear. That's what we already seen in the diagram. So I already explained to you. So this outer row rivet is subjected to single shear. This one, because the here it is covered by only one cover plate, that's why it is subjected to single shear. And these two rivets are subjected to double shear. And also if I take the repeating section here, this is our repeating section. Out of these all rivets, this rivet is subjected to single shear and these 4 rivets are subjected to double shear. So that means you have total 5 number of rivets are there. Out of these 5, one rivet is under single shear, 4 rivets are under double shear. So therefore I will estimate the shear strength based on these conditions only. So that's what I showed here. That's what I written here also. So the rivets in the outer row are subjected to single shear. At the same time, the rivets in the middle and inner rows are subjected to double shear. So let N1 is the number of rivets subjected to single shear per pitch length, and N2 is the number of rivets subjected to double shear per pitch length. Then again, this is the condition. When this is going to happen, when the strips have equal width. That means this some rivets are in single shear and some rivets are in double shear when there are unequal width strips are there. If they are equal width, obviously all the rivets are subjected to double shear only. That means if all the rivets are covered by the 2 cover plates, they are in double shear. So in this particular joint, first what we have seen is the outer cover plate is not covered for the outer rows. So therefore, they are the rivets in the outer row, they are subjected to only single shear. So then I want to estimate that. So for boiler joint, the shear resistance of one rivet in single shear is given by, we know this formula. This is nothing but 5A4 D square into tau, where D is the diameter of the rivet and tau is the allowable shear stress in the rivet. So this is the case for the single rivet in single shear. Suppose if it is a double shear, generally what we do is we need to multiply this one by 2. But in case of boiler joints, they won't take it as the shear resistance in double shear is not equal to twice the shear resistance in a single shear. They will take it as 1.84 times. Also, the shear resistance of one rivet in double shear is assumed as 1.875 times. Instead of 2 here, they will assume it as only 1.875, not exactly 2. So that means this is somewhat a conservative approach here. So they will assume it as, instead of 2, they will assume it as 1.875. So therefore, if I know these conditions, then I can easily estimate the shearing strength of the rivets here. So that is, this is the shearing resistance of the rivets which are under single shear, where N1 is the number of rivets in single shear and N2 are the number of rivets in the double shear. So this is the shearing strength for a single shear. 5/4 d square into tau is the shearing strength for single shear. Then if I multiply the number of rivets in single shear, I'll get the shearing strength of the rivets which are in single shear plus the shearing strength of the rivets in double shear. So here instead of 2, we are in the case of this boiler joints, the boiler code proposes only 1.875. So the strength of the rivet in double shear is 1.875 times the strength of the single shear. So therefore, this is going to be the shearing strength of the rivets which are under double shear. If I add these two, I'll get the shearing strength of all the rivets now. Now, I'll take this expression and I'll equate this one to the tensile strength of the plate based on the outer row section. If you consider section in the outer row, this is the equation. So now, I'll equate these two. By equating these two, I'll get an equation, or if I simplify this, I'll get an equation for the pitch here. So in this, everything known. N1 is the number of rivets in single shear, N2 is the number of rivets in the double shear. Before this identifying the pitch of the rivets, we already calculated the diameter of the rivets, and we know what is the allowable tensile shear strength of the rivets. And similarly, we already estimated T is the nothing but the thickness of the boiler shell. First step, in the first step itself, we estimated this. Even sigma T also we estimated there. Plus D also we know to us. So now with this, I can compute the P value. Now, if after computing this P value, now I have to compare this P value to P min, P minimum, and P maximum. So you have a conditions for P minimum and P maximum. P minimum is going to be 2.252, that is given in the data book, 2.25 to 2.5 D. So then if this P is more than this, then okay, I will take this. And not only that, I need to verify this also, P max condition also. If this P lies within this range, P minimum to P max, simply I will take this one as the pitch value. Maybe by rounding up to the nearest numerical. So let us say, if I got something like 24.32, something like that, I'll make it as 25. Like that, I'll round it off. By rounding it up to the nearest value, I'll take the pitch value. But if this P falls outside this range, that means if it is less than this minimum value, I have to take the minimum value as the pitch value. Or if it falls outside this maximum value, then I have to take the P maximum for the pitch value. So like this, I can estimate the pitch value. So that's what I showed it here also. The pitch obtained by earlier equation as maximum and minimum limits also. According to Indian boiler regulations, the pitch of the rivet should not be less than 2D to enable the forming of the rivet head. So that means if the pitch value is less than 2D, then what happens is you have a rivet head is there. So suppose here this is my pitch value. So now I have a rivet here, I have a rivet here in the pitch value. So then what is the diameter of the rivet? So here I have a head is there, something like this. So if I form these two heads, they will become overlap to each other. So they may overlap against each other. So therefore, this rivet head forming is going to be very difficult when if you take this P minimum is less than this 2D value. So that's why this is the minimum pitch we need to consider. And at the same time, in order to provide leak-proof joint, the maximum pitch is given by, this is the condition. P max is equal to C into T plus 41.28. Again, the values of C are given in the table 9.7 of your design data book. So that's what I mentioned. Right? So like this, we can estimate the pitch value. Once I have estimated pitch value, then I need to estimate the remaining things in our joints. So what are the remaining things? Clear these things. Okay, so now what only left out things are PT, M and T1. So this PT, T and M are, there is no calculation or nothing are required for this PT value and M value and thickness value. So straight away what we'll do is we need to use the data book to identify these values. So I'll show you that to you again going to this. Okay, I'll come out of this presentation. Now again in the data book you can see that if you open the next page, in the next page first condition is, he has the first thing what he has given it is, this is the column which is corresponding to the your PB value. You can see this PB is there, PB is there. So in this first one is same type of riveting, and this condition is for the zigzag type of riveting. Again in this you have two conditions. One is first condition, what is there? Equal number of rivets in all the rows. So that means there are number of rows in the outer row is same as the number of rivets in the inner row and middle row. If that is the condition, I have to take PB equal to 2D. If it is chain riveting, if it is zigzag riveting, I need to take PB as 0.33P plus 0.67D. So P already we estimated now in the previous step. Then you have D also. Then you need to use this equation. But in the joint, whatever right now we are discussing, in that it won't satisfy this condition. It is satisfying this condition. That is, the number of rivets in the outer row is half of the number in the inner row. So this is the condition what we are discussing now. If that is the case, again we are not using the chain riveting. So like I already shown to you, it is a zigzag riveting. For zigzag riveting, you need to use these conditions. That is PB1 and PB2. You have two conditions, PB1 and PB2. Why it is PB1 and PB2? If you look at the diagram here, so maybe he has given the diagram also. See, you can clearly see that he has given the picture of that one joint also here. Clearly you can see that here. So this is going to be the pitch value. Then your PB1 is nothing but the distance between these two, it is PB1, and the distance between these two, so that is outer row to inner row. Outer row to the middle row, I'll take it as PB1, and middle row to the inner row, I'll take it as PB2. So for those two conditions, he has given the values here. So based on, so only thing what you need to look at it is these two conditions, whether it is chain riveting or zigzag riveting, you need to look at this condition, and whether this is subject, this condition is satisfying or this condition is satisfying. You need to look at those two conditions. Based on that, you need to pick the formula here. So once I done that, then thickness, last step is thickness of the cover plates. So thickness of the cover plates is here when there is a single cover, double cover, again single cover with outermost having row having alternative rivets. So like that, different conditions are there. So in those conditions, based on that, he has given the formulas for T1. So T1 is equal to 0.1125 T, or when it is a single cover plate. When it is a double cover plate, your T1 is 0.625 T. Yeah, I know, Mr. Sivaprasad, you can wait. You have a next class at 3:30, right? Sorry, not 9:30, 10:30 you have a next class. Just now it is 10:17 only. I am looking at the watch only. You joined 20 minutes late, so that's why I am taking 5 more minutes more. If you want, you can leave, no issue. Right? So like this, you need to use all these formulas to compute the thicknesses. So he has given all the conditions for the thickness. So for different cases, so you have to pick the respective formula to find out the thickness values. So like this, I can design the joint. So once I design the joint, then after that, simply I cannot leave that. It is not a completed one. So the process is not yet completed. After designing it, after identifying all the values, again I need to estimate the efficiency of the joint. So after estimating the efficiency, then whether it is satisfying my required efficiency or not. At the beginning, I have taken the efficiency in calculating the T value. I use the efficiency of the longitudinal joint. Whether it is satisfying that condition or not, I need to check that also. So that means if it is a triple riveted joint, your efficiency should be 0.8 to 0.9. If it, that is, whatever design you made it, if it is satisfying that condition, then you need to say, okay, your design is correct. If it is not fall within that range, then again you need to redesign the joint. Maybe You need to modify some of the parameters. Based on that only you need to design the joint. Right? So like that you can do that. So this is the procedure to design the lap joint. Sorry, not lap joint. It is a butt joint of a longitudinal joint. So maybe in the next class we'll see. First we'll see some problems on this, 1 or 2 problems. Then we'll move on to the next one, that is circumferential joint. Okay. So I'll stop now. Maybe we'll continue in the next class. So now you can leave. You give the attendance and you can leave the class. No issue.